dear Vice Rector, for the warm greeting. You see nowadays representative of 9 institutions from Lviv, from Kiev, from Kharkiv, Ivano-Frankivsk are joining us now. So these institutions are Lviv Polytechnic National University, Ivan Franko National University of Lviv, Astronomical Observatory, the Taras Shevchenko National University of Kiev, Astronomical Observatory, Space Research Institute National Academy of Sciences of Ukraine, Main Astronomical Observatory of National Academy of Science of Ukraine, Igor Sikorsky Kiev Polytechnic Institute, Vasil Stefanik Prekarpathian National University, Institute of Condensed Method Physics, and National University of Kharkiv Astronomical Observatory. So you see the great interest for your person, for your scientist result, and for your Nobel lectures. Let me tell you a few words about our Nobel lecturer. Dr. Mather is an American astrophysics, cosmologist, and Nobel Prize in Physics laureate for his work on the Cosmic Background Explorer satellite, COPE, with Dr. George Smoot. His work helped cement the Big Bang theory of the universe. According to the Nobel Prize Committee, the COPE project can also be regarded as a starting point for cosmology as a precision science. Dr. Mather is a senior astrophysics in the NASA Goddard Space Flight Center in Maryland and an adjunct professor of physics at the University of Maryland College of Computer, Mathematical and Natural Sciences. In 2007, Time magazine listed Mather among the 100 most influential people in the world. In October 2012, he was listed again by Time magazine in a special issues of New Space Discoveries as one of the 25 most influential people in space. So, with great pleasure, I will give a floor to Dr. Mather. You're welcome.
Thank you so much for the kind introduction. I am thrilled to be able to speak with you, and I have some pictures and PowerPoint to show you, and I will be happy to have questions and discussion afterwards. So thank you all for coming. Let me see if I can share my slides because I have beautiful pictures to show you. So one moment, still trying to do this. We're having a problem with sharing the slides today. And one moment here. I think this one might work. Do you now see my screen here?
Anyway, yes. Excellent. Now we see. You're welcome.
Okay, so what we show here is the great James Webb Space Telescope in outer space. It is, as you know, a joint international project of the NASA with European and Canadian space agencies. It has taken over 20,000 people to build it. It has been started as of today, actually is the 27th anniversary of the phone call that started my work on the project. So it is also now available to all astronomers around the world. Anyone can send us a proposal to use the telescope. And all of the data will become public. So you will be able to get all of them from the archives as well. So what you see in the picture is the great golden hexagon. It is 6.5 meters across. It collects the starlight and the galaxy light and focuses it into the instrument package. Underneath the telescope is a 5-layer sunshade. It's actually metallized plastic. It's as large as a tennis court. And below that is the warm portion of the spacecraft that provides all the rockets and telemetry and power and things of that sort. So I'll show you more in a little while. But let me first back up a little bit to my own history. Come on, machine. To how did I get started to become a scientist? So everybody seems to think scientists are different from everyone else. Well, I was just a curious child. This is the farm where I lived when I was a small boy, and even up until high school. But it's also not an ordinary farm. It's a research farm where my father was investigating dairy cows and how to get more milk and better milk from the cows. But for me, it was a place to read books and play with hammers and nails in the shop. So building things and learning things from books was what I got to do as a child there. And I never expected to be working for NASA or to be a Nobel Prize winner, but that's how it has turned out. Anyway, so when I was a child, I was unaware of the progress that had already been made 2,000 years ago. You probably already know of a poem by Lucretius from BC times. Here is his version of the meanings of the atomic theory. People already suspected that the material things you can see are made of tiny invisible particles and that they stick together in patterns to make what we see. So he wrote about this. He was aware that combinations of small things to make large things would make all the complex systems that you see today. And that, of course, then when they get big enough, we human beings can give them names. Then after a while, they disintegrate and disappear, and it all returns back to be recycled. So that's very similar to the story that modern science has given us, but we have, of course, much more detail. So the old view of the universe and life was we certainly don't understand it, and life must be very unlikely. Before we knew there were planets everywhere, we thought planets were very unlikely because we could not imagine how this all might have happened the way that it has. And in fact, there is even a very mischievous idea that the universe is as it is, because if it were not, we would not be able to be here to talk about it. That's called the anthropic principle. I don't think that's a very useful idea. But at any rate, it was thought for many, many decades, maybe perhaps centuries, that the origin of life must be so unlikely that it could not have started here and must have come from somewhere else. Now, today, of course, we still do not understand where life came from, or the nature of the great theory of everything that would tell us how all the physical laws are supposed to work together. But we do have now a different perspective that perhaps as soon as life is possible, that life will begin to grow. And that if there is an unstable situation, say an energy source, and the proper molecules can be combined together, then it might not be so very unlikely that life could occur wherever it's possible. So to give a little bit more detail, our story of the universe is the universe is expanding now. It was very smooth and very hot when it was young. It has been very unstable. So it spontaneously reorganizes itself into complex systems. And of course, that's thermodynamically favored. Thermodynamics is not against this. In fact, astronomers now say that gravitation causes systems to have negative specific heat. Negative specific heat means they spontaneously heat up. Of course, the universe is very old and might possibly be infinite in extent. So that means that even very unlikely situations, such as we think ours is here on Earth, can still be possible to occur. We have learned in recent years about the nature of information. And in life, we see it as stored information governs the growth of living things. The DNA molecules in our living cells carry the information, and there are systems in the cells that decode that information and instruct them on what to do so that they can function and maintain themselves. And this stored information enables the possibility of evolution, unlimited complexity of life. And here you are and I are because of this possibility of stored information. We also, as engineering students and scientists, have learned that there are feedback loops, control laws that stabilize the systems that have been developed. For instance, a living cell will have numerous feedback loops in it that maintain its shape and function, even though the atoms and molecules come and go. My own body has been maintained in about the same shape now for 76 years. So that's a remarkable story, even though most of the atoms have been replaced. So how do physics laws work this way? Well, number one, we have quantum mechanics, which is still quite mysterious to people because it tells us things about non-local activities. And that's certainly possible because every individual particle seems to behave like a wave, a complex wave, in fact. So the quantum mechanics is the set of laws that give shapes to the atoms and molecules and tell them how to stick together to make larger things. So when you say, is quantum mechanics important? Yes, it is. We are here because of it. We have a theory of relativity, which describes gravity, and that is, of course, the source of the negative specific heat that I mentioned that causes things to become complex. We have, for well over 150 years, we've understood equilibrium thermodynamics and how things happen. We know that entropy always increases. And so if something happens that appears to us to have decreased entropy because it's very orderly, then it means that somewhere else nature has put the disorder. So for instance, when an ice crystal is formed and becomes very orderly, then we see that the heat that it gave off when it froze is stored somewhere else. So on the other hand, we now get to something we really do not understand very well, non-equilibrium thermodynamics. So you and I are one of nature's ways to increase entropy. So this leads us to the question of, is life a thermodynamic imperative? In other words, will it always occur given a chance? So we have a little bit of evidence from our geologist colleagues and our biologist friends. We know that all known living materials shares a very similar kind of biochemistry and genetic code. So there are various possible interpretations. One is that all of us are descended from a single first living thing, or another possibility is there were many, and our particular version happens to be more able to reproduce, so we're here because of that. Or it's even possible that it's happened many times and nature has always found the same answer to do this. We don't know how to figure this out. We do not know how to calculate. And if you are looking for a good hard problem to work on in the next centuries, this is one of them. We do not know where life occurred for the first time here on Earth. One favored explanation is under the ocean, where warm water comes bubbling up, enriched in all kinds of interesting chemicals. We do have one observational data point, which is that we have geological signs in fossils that life occurred soon after the oceans occurred here on Earth. It's very hard to tell because there are not very many rocks that are old enough to analyze. So that's almost 4 billion years ago. It took about 2 more billion years for complex life to occur with multiple cells, and then things with eyes and legs and teeth that are recognizable to us as animals only about 500 million years ago, and our human ancestors show up in the fossil record only 500,000 years ago. So, of course, we don't know how this happens. We're very interested. It's one of NASA's most interesting topics. because we, NASA, can go looking at other planets here in the solar system, or even looking for signs of life on planets around other stars. So one of our major challenges for astronomy. So just to summarize what I think everyone here knows, astronomers look back in time by looking at things as they were when light was sent out. Light travels very fast, 300,000 kilometers per second. But if you're looking very far away, you're looking very far back in time. So back in 1929, Edwin Hubble drew us this graph. This is the first time that we knew that the universe even has an age. What he plotted here are little dots indicating the apparent distance and the apparent velocity of going away from us for all these galaxies. So you can see that except for 4 very nearby galaxies, all of them are going away. You can see that there's a trend that the farther away they are, the faster they're going. So if you divide this distance by the speed, you can get the apparent age of the universe. Now, back in 1929, there was a mistake. And so it seemed for a long time that there are stars that are older than the universe. But now we found out that Hubble's distance scale was incorrect. By the way, this expansion law was predicted by Georges Lemaitre, who was a Catholic priest in Belgium, as well as having a doctorate in mathematics from MIT. So he used Einstein's equations to predict that this must be true, this graph. But Einstein did not agree. And he did not even agree after he saw the measurements. He had to be shown that there was a mistake in his theory. At any rate, we now know the universe is expanding, and we've measured this graph much better. So it was soon predicted in 1948 that if the universe is expanding, then it must probably be very hot when it was young. So as was mentioned in the introduction, George Gamow, Ukrainian scientist, was working here in the United States, and with Ralph Alpher and Robert Herman, predicted that the cosmic heat that was there in the earliest moments of the expanding universe should still exist. And they predicted the temperature, and they got it about right. The radiation was discovered in 1965, and in 1974, after my thesis project in Berkeley had failed to function properly, I got a chance to work with NASA people to propose a satellite. And here it is, the Cosmic Background Explorer in orbit. It was launched 15 years after the first idea, and it measured the cosmic background radiation spectrum immediately, confirming that this expanding universe story is correct. And 2 years later, we also made the map of the hot and cold spots. And this is the work that led to the Nobel Prize in 2006. So this is the map of the sky as seen with millimeter wave equipment on the Cosmic Background Explorer satellite. There are hot and cold spots in the pink and blue blobs that represent tiny variations of temperature. The average temperature of the sky is about 2.7 degrees Kelvin. And the variations are about 1 part in 100,000. That is to say, 30 microkelvin. So when Stephen Hawking saw the map, he said it was the most important scientific discovery of the century, if not of all time. So why would he say that? Number one, our understanding is that gravitation acting on the denser areas was able to stop the expansion of the material and pull ordinary matter and cosmic dark matter back together to collapse into objects like stars and galaxies. So we are here because of the spots on this map, combined with the action of gravity. I guess number two is most of the spots themselves are due to cosmic dark energy. Number three, we now know there is something called cosmic. I said that wrong. Most of the maps on the spots on the map are due to cosmic dark matter, which has gravity and can help the expansion stop. This pattern of the spots is also influenced by the cosmic dark energy. which we now know is making the universe accelerate in the expansion for the last 5 billion years. So if we understand this, then we should be able to predict what will happen, how will the galaxies grow, and we even can make computer simulations. But if you really want to know, you have to observe the sky. So, of course, we launched the Hubble Space Telescope. It was launched about 5 months after the Cosmic Background Explorer, and it is up in space and still working beautifully, of course, because 5 times astronauts have been up to visit it and improve it and fix it. So it's up there working. One of the first results from the observatory was that the galaxies that they saw were not the very first galaxies. It was hoped that Hubble Space Telescope would be able to see the first galaxies growing from the primordial material. And the answer was no, it's not powerful enough to do that. So please build us a new telescope that's able to see farther back in time, farther out into space by using infrared light. And we'll come back to that. So here is the answer to that request, the Great James Webb Space Telescope. It is, as I mentioned, an international partnership. Our main aerospace contractor is Northrop Grumman Space Systems, located near Los Angeles, California. We have instruments that come from Europe and Canada to cover the entire spectrum range from 0.6 micrometers, which is orange, and you could see that with your eye, all the way out to 28 micrometers, which of course you cannot see. So operations of the observatory are carried out at the Space Telescope Science Institute in Baltimore, Maryland. To summarize, what we see here is the telescope that I already showed you. The telescope operates at a very low temperature, about 45 degrees Kelvin, so that it does not emit its own infrared. It was launched on December 25, 2021, to orbit around the Sun-Earth Lagrange point L2, and I'll show you where that is. But the launch was perfect. It was a French launch vehicle called the Ariane 5, and because it was French, that we went to French Guiana for the launch site. So that's where the commercial rockets go up from Europe, at least one of the sites for them. And we were very pleased with the rocket because it worked perfectly, put it exactly where we wanted to go. Here is the place we have sent the observatory. We orbit around a place called Lagrange point 2. It is in a straight line from the sun to the Earth to the Lagrange point. We orbit around the Lagrange point, of course, because we don't really want to be in the shadow of the Earth. We need solar electricity to run the observatory. But it's a great place for the telescope because in that direction, we can see the sun, the Earth, and the moon all in one side, and a single-sided umbrella, a single-sided sunshade can protect us from the heat of the sun. Here is our scary movie. This is the unfolding of the telescope in space. It's actually took place over the time period of 2 weeks. So this is much speeded up so that you can see it. The first thing that we unfolded was the solar panels to get electricity for the observatory. The second was the transmitter receiver antenna, which operates at microwave band called Ka band. Here we're separating the telescope from the warm part so that it can cool down better. Here we are unrolling the covers over the sunshade. You can see an extremely complicated design here. And if there had been any easier way to do this, we would have found it. But the astronomers said, we need a big telescope, we need a cold telescope. And so if you need that, then you have to build it this way. So the last step is to unfold the mirror itself. When we reach this point, it is still not ready for observation because it is not focused and it is still warm. And that's what it took most of the first 6 months to get it all set up, all of the instruments checked out, telescope cold and all of the necessary parts prepared and ready for operation. So you see there are 18 golden hexagons, and all of them must be adjusted so that they function as though they were part of a single large mirror. This is the collection of instruments that we have on board. There are cameras and spectrometers to cover this whole wavelength range, because of course, when you start with an idea to build a telescope, you don't really know what astronomers are going to need and want to do 10 or 20 or 50 years later. So it's a very general purpose set of tools. The camera covers from 0.6 to 5 microns, and it has multiple detectors. There is a near-infrared spectrograph, which comes from Europe, and is able to observe 100 separate galaxies at one time. We have a mid-infrared instrument covering 5 to 28 microns, with a spectroscopy and imaging. And we have a fine guidance sensor and a near-infrared slitless spectrometer that come from Canada. So I'll show you a little bit in the results what these instruments can do for us. So just to back up, however, why do we study infrared? This is one of the examples. There's a star, brand new star, being born inside this dust cloud. And why, of course, would a star be born inside a dust cloud? The main reason is that the dust is able to cool off the gaseous material and let the temperature go down so low that gravitation can overcome the gaseous pressure and pull the material together to compress it into something that will become a star. So right down inside of this dust cloud is a new star being born, and we can't see it because the dust is too opaque. But even with the Hubble Space Telescope, there is a little bit of infrared capability. So this is what the Hubble telescope can do with infrared. And when we see now that there's a central star, along with 2 jets of material that are coming out, propelled out from the north and south poles of the new star, we imagine that there are planets being born at the same time around that new star, but it's hard to prove that yet. So that's number one. Reason to use infrared is to see through the opaque clouds of dust. Number 2 is to see things that are not warm enough to emit their own light because they're not, well, anyway, they're just too cool. So, of course, you and I are emitting vast amounts of infrared power ourselves. Each one of us is emitting about 500 watts of infrared power, and nobody notices. But anyway, it's there. Here is an object called the Southern Ring Planetary Nebula. It was named this way because early astronomers thought it looked like a planet, but it is not actually a planet. It's a cloud of dust and gas that's being expelled from an old star right there in the center. In fact, on the right-hand side, you see the mid-infrared picture, and you see that there are 2 stars in the center. The faint one is the one that you can't even see on the left side, and it is hidden by its own dust clouds. At any rate, here is the material coming back out into space. This is one of the ways that the heavier elements are liberated from stars so they can be recycled into new generations of stars and planets. As you know, the Big Bang only gave us hydrogen and helium, but when you look around the building that you're in, you see calcium and oxygen and phosphorus and carbon and nitrogen and oxygen. And so all of those chemical elements were made inside stars by nuclear reactions, and they had to be liberated so they could be recycled to form you and me. The third reason, here is the magnified picture. The third reason to study infrared is that space is expanding, or alternative way of describing it is that distant galaxies appear to be running away from us very fast. And this is called the Doppler shift. So as we see distant galaxies receding, the light that we received from them is stretched out as well, and stretched out in wavelength. So by the time that the galaxies are very far away, we receive infrared light that started out as ultraviolet. So infrared telescope to see far back in time and far out in space. So here's an example of our first images that we got from the Webb telescope. This was released on July 11th by President Biden, and it is a picture of a more or less special spot in space. It's special because there are, it is special, it is special because there are all these bright galaxies in the middle. Let's see if I can show you better here. So here in the middle is a collection of bright galaxies. They are so bright that they have a lot of gravity. And the gravity of bright galaxies is able to bend light. So you see many interesting, strange objects here. This is an arc. Here's another one. Here are some more. These are magnified and distorted images of much more distant galaxies. They're magnified and distorted by the gravitation of the bright nearby ones. So this is an extra lens on our telescope. We have locations of hundreds of these in space, and so we know where to look when we want to see even more distant galaxies than we know about. So we already knew when we got this picture that there would be galaxies everywhere. In fact, this picture shows galaxies that the Hubble could not see. So why do we use spectroscopy? We spread out the light of stars and galaxies into its colors. And of course, the human eye can only see red, orange, blue, and violet in a certain order. The Webb telescope can be able to see many more colors, but they're colors that are invisible to humans. So we have to change the color scale and replace the observations we take with colors that humans can see when we draw you a picture. So here's an example. I showed you that there were arcs in the sky, and we've sent the light from those arcs through the spectrometer to get their chemical constituents. And we find out that this object has hydrogen and oxygen in it. We see that the two objects have the same wavelengths, the same chemicals in them. So we say they do seem to be two images of the same more distant object. And we see also that this distant object has hydrogen and oxygen. So we already know that this is not a primordial galaxy. This is a galaxy which has been enriched by the nucleosynthesis products of stars that got old and either exploded or send out their light in those kinds of nebulae like I just showed you. So another way to find these most distant objects is to take this picture and look for the smallest, reddest objects on them. And so we identified 4 little tiny red spots, and we spread out the light in the spectrum again. And each one has its own set of colors. But you see, again, we see hydrogen, oxygen, hydrogen again, hydrogen and oxygen together, but the wavelengths are different. So this tells us that these objects are moving away from us with different speeds. So this particular one is moving away in such a way that we've measured the redshift, that is to say, how much has the wavelength increased of 8.5. So this is an object that's about 700 million years after the expansion began. We can analyze more of the chemistry. Here's one of these objects. Spread out the light again, we get not only the hydrogen and oxygen, but even neon is seen in the spectrum at around 3.7 microns wavelength. So we've also imaged a thing we call the sparkler galaxy. This particular object is imaged 3 times. And the most magnified image is number 2. And you can see this early galaxy has little spots on it. And these are called globular clusters. Here in the Milky Way, we have many, many globular clusters, maybe 100 of them at least. So each one is made of 100,000 stars or so. And here we see them in an object that was, as it was, about 9 billion years ago. So this is the farthest away we've ever been able to see these objects. They are perhaps even precursors of galaxies. Maybe they were formed before the galaxies were formed. This is a beautiful object which is close by. There are 5 galaxies in here. The one over here in this area is called Stefan, is very nearby, and it's so bright and so close that we can see individual stars, individual red stars in its picture. The 2 galaxies in the middle are, the 2 galaxies in the middle here are interacting with each other. Stars do not hit each other when galaxies collide, but the gaseous material does collide with other gaseous material. And here it is prompted to form new generations of stars in these reddish areas. The galaxy at the top is not only interacting with the others, but it also has a black hole right in the middle. And how do we know there's a black hole in the middle? Number one, it looks extremely bright. So much brighter than any ordinary star would be at that distance. Also, we can make a spectrum of the light from that area and measure the velocity of motion of stars orbiting around it. And so we do that, and we spread out the light. In this case, we can have a tool called integral field spectroscopy. So we can make a spectrum of every pixel around that particular black hole. And we see the different kinds of atoms and molecules orbiting around and where they are and how fast they're moving. So we can calculate from the rate of motion what is the mass of the black hole in the middle. And it's a lot. I don't know the number. We can also even spread out the light to see the spectrum in the mid-infrared. And here we see something called silicates, as well as additional atoms that I didn't show you before. We have argon and sulfur orbiting around there. This is an area which has clearly been enriched by previous generations of stars that died. But silicates are important here because this is a sign of dust clouds. Dust clouds, as I mentioned before, are able to produce new stars. And if they're forming very near enough to the black hole, after they form, they can fall in to the black hole. This is a remarkable picture called the Cartwheel Galaxy. This is a place where this galaxy in the upper left went flying right through the center of this galaxy in the middle. And what we see is this splash, the material that was expelled from the center of the galaxy and went out to make new generations of stars all around the edge. So quantitatively, we can now understand how do galaxies form stars by looking at these special examples. Of course, you can also see that in the background there are small red specks and small galaxies everywhere. They're just galaxies everywhere in this picture. Close to home, this is a galaxy called M74. It's had been processed by a person who's not a scientist, but has learned how to do beautiful image processing. So she's processed our picture to show you the nature of holes in the galaxy. In the original pictures of visible wavelength images, this is a spiral galaxy about this big, but now we see there are holes. So why do we have holes in a galaxy? It looks like a slice through a sponge. In a sponge, of course, the holes come from gaseous pressure that pushes the liquid material away as the sponge is being made. Here, the pressure comes from bright new stars that were born in the center of the hole. They produce so much energy that they can heat up the residual gas that's there and push the gaseous material away. So we end up with a hole, and we also get new stars. We get new stars being born around the edge of the hole. Here is the Carina Nebula, one of our most beautiful pictures already. So many people are using this on their screensavers on their computers. At any rate, this is a kind of cosmic recycling center. This is where the old enriched gas that's been filled up with dust from previous generations of stars is now being turned into new generations of stars. In the top, you see some bright stars. Up here, these are bright new stars, and they are producing this kind of immense amount of heat, which is shining down on the dust cloud and causing these wispy blue trails of material to come up as the dust cloud is being vaporized. Inside the cloud, you see some remarkable images like this one, where clearly a new star is being born, another one down here, a new star being born in there. And we're just beginning to understand how this works. At first, we start just by counting the new stars in there and learning how they grow. We hope to see soon enough that there are signs of planets growing around these new stars. Here's a magnified picture just showing you what we can see in the cloud. By the way, this is another example of stars putting jets of material out, like one of those first pictures that I showed you. This one is sending out jets, but it looks like this jet is being bent around as though there's a wind blowing from above down towards this and pulling the jet of material with it. So here in the solar system, we've been observing as well. This is a map of Mars on the left, and we're now able to make a similar map from here with the Webb telescope to measure the temperature of Mars and see how it changes with location on the surface of Mars. So, of course, we already knew a lot about Mars, but we're just proving our technology. But we also got a spectrum of Mars, which we can analyze to find out what are the atmospheric constituents. I think everybody knows there's a lot of carbon dioxide on Mars. There's a little bit of water in the atmosphere, not very much. And there's even a little bit of carbon monoxide and oxygen, although that's not on the spectrum here. If you want to go live on Mars, then it's nice to have carbon monoxide and oxygen in the atmosphere. If you can increase the concentration, then you can, say, using a zeolite material to capture them, then you could breathe the oxygen and you could burn the carbon monoxide as a fuel. So we've attacked an asteroid, as you know. We sent a double asteroid redirect test mission out there. There's a pair of asteroids out there that one is orbiting around the other. And so we dropped a large piece of metal into the small asteroid to see how its orbit would change, and therefore measuring its mass. We also wanted to see what would happen. Would material come splashing out? And yes, indeed, we do see that debris has come out of the asteroid. So now we're learning how to protect the Earth from dangerous asteroids by doing this test. We have observed, of course, everything else that we can in the solar system. It turns out that Jupiter and Saturn and outer planets are more or less in the same area of the sky at the moment, and we can see them. Here is an infrared picture of Jupiter, and you see the great red spot is no longer red in this image. You see a tremendous amount of detail. The picture is very sharp, and you can see even auroras at the north and south pole that are due to electrons excited by the magnetosphere of Jupiter crashing into the upper atmosphere of Jupiter. We will be looking at Europa. Europa is a very interesting satellite of Jupiter. It was discovered by Galileo himself in 1610. So we sent an observatory called the Galileo mission. In the year 2000, it took this picture on the left. And we see that Europa is a satellite covered with ice. And underneath the ice, we now know there is an ocean. Once in a while, with the Hubble telescope, we can see water vapor is coming out from the cracks between the blocks of ice. So we're going to send a NASA probe out there to fly through the plumes of water vapor to see if they have any signs of molecular life. Do they have organic molecules in that water? So we'll find out. In the meantime, we're going to be watching it with the Webb telescope, which has the ability to see water molecules in space. We are going to be watching Titan, which is a satellite of Saturn. Europe sent a mission called the Cassini and included a lander called the Huygens lander. And so we landed on the surface, took a picture. We see rocks on the surface of Titan. By the way, it was a joint US and European mission, the Cassini mission. Anyway, the lander got pictures. We know there are interesting surface features. There's lakes and rivers and rain and clouds. So there's interesting weather and geography there. It's so interesting that we are sending another probe out there, which will include a small helicopter to fly around and examine the surface nature and eventually prepare the way for searches for life of a new kind on the surface of Titan. Do you think life should occur in a place where there's liquid hydrocarbons and hardly any water? Well, most people would say no, but we should look. Here's Neptune with its satellites, and you can see Neptune has rings. We are observing planets around other stars in this way. If you are fortunate and looking at the right time, sometimes a star will have a planet that goes in front of it and intercepts some of the starlight. And the animation is showing you that you could imagine a case where the planet has different apparent size according to what wavelength you're using. So why would that be? Well, if the planet has an atmosphere, some of the light of the star will go through the atmosphere on its way to the telescope. So you can now measure the apparent size of the satellite, of the planet, by how much starlight it blocks, and in that way study the chemistry of the atmosphere of a planet of another star. So this is a prediction for what you would be able to do if you could block some of the starlight. If you could examine the starlight going through the atmosphere of an Earth-like planet with an atmosphere like ours, and it would show that you should be able to detect carbon dioxide, carbon monoxide, methane, water, and oxygen and ozone. But this is an extremely difficult project to do because the Earth is actually very small, and the amount of light that can go through its atmospheres is even smaller yet. So this is not a feasible experiment for this mission, but we do have hopes that we'll be able to see the water molecules, if there are any water molecules in another little planet around a small star. Small stars are called M stars. They're very small. Planets are very close to them. And we even have some that are well known already. There's a system called the TRAPPIST-1, where there are 7 planets already known, and 3 of them might be about the right size and temperature to be like Earth. I would predict that there's no atmosphere there, but we will find out by looking. We did already measure this in a test case on a planet that we knew about. This is a very large planet, very close to its star, so it's very hot, but we definitely proved that the technique works, and there is indeed water vapor in that atmosphere. Perhaps you should call it steam because it's so hot, but at any rate, the technique works, and we hope to be able to tell you soon whether planets out there do or do not have an atmosphere. So that completes the story about the Webb telescope. There are always many more things to think about, but just let me invite you to follow us on the internet with our social media, our Instagram pictures, our Facebook, all the things that people use now to share individual images. And we have a blog that comes out about once a week with new announcements. You can follow all of these things if you look them up with a search engine like Google. So let me stop here and have questions from you all, and we'll see what happens next.
Yeah. Dr. Mather, thank you very much for your impressive and very interesting, inspiring lecture. So thank you for your new view of universe and life. Yes, you see, it was very interesting and impressive for us. More than 25 people are online with us and more than 100 people are here in our assembly hall. So it's a good time to ask questions to our case speakers. So I hope we have approximately 10-15 minutes to ask your question, and I invite all scientists, PhD students, young people to be active and use a unique chance to ask questions to our Nobel lecturers. So you are welcome. Who would like to be the first? You are welcome.
I'm sorry, that microphone is muted. I can't hear it.
Try to be louder and please represent yourself. Introduce yourself.
So I could not hear the question and microphone was muted, I think.
So one more time.
Yeah.
So I'm associate professor of National University Lviv Polytechnic. And first of all, thank you so much for your amazing presentation. I believe that today's event will be a booster for all our academic society, especially for young people. And I have a question. The visible universe, including Earth, the Sun, all stars and galaxies, makes up less than 5% of the mass of the universe. The rest of the universe is a mysterious, invisible substance called dark matter. So my question is, will James Webb Space Telescope be able to help us to understand dark matter or dark energy? Thank you.
Okay, excellent question. And of course, we certainly will try. We will be observing the effects of the dark matter in places like the magnifying galaxies that I showed you at the beginning, or sorry, the first picture that the president released, because we can measure the gravitational effects of the dark matter, and we can find out more about where it is and what it does. We would really like to know its properties. Is it hot? Is it cold? The current understanding is the dark matter is cold, which means the particles are not moving very fast. But it might not be the only kind. So we hope to see evidence be able to test that question. The dark energy will certainly be measured more precisely with this equipment by the same methods that were used to discover the dark energy, which is to the measurement of standard supernovae. You know, we use the brightness of standard stars and in order to measure their distance. And so we will try all of the same methods again, and we think that they work better with an infrared telescope. So the answer to your question is yes.
Thank you so much.
I'm PhD student of the Department of Electronic Engineering at Lviv Polytechnic National University. And firstly, I want to thank you very much for interesting, informative, and discovery report presentation, your individual experience, and the most important result of your research. So I have some questions. James Webb Space Telescope can detect only objects like about hundreds million years million years. I'm so sorry. I'm so sorry. Yes, of cosmic time. Yes, after the big bang. what preceded the cosmological singularity on your mind, and do you believe in the multiverse theory? Thank you.
Okay. If I knew the answer to your question, I would have another Nobel Prize. But in the short version is no one really knows what came before the expansion of our current universe. The way I think about it is if you imagine the movie of all the galaxies running away from us, and then you run the movie backwards, the galaxies collide, the atoms collide, the temperature goes up and up and up until we get to a place where we no longer understand what physics tells us. We can imagine getting to a temperature and density which is so high that gravitation actually bends space-time, and even time and space do not mean the same thing that they do now. So we need a story of quantum gravity before we can really resolve your question. So far, we have no theory that is very popular with astronomers. All of the theories have some problem. So the other challenge is that we don't really have a way to tell the difference between one theory and another through observation, because everything that must explain what we call the Big Bang, the expanding universe, they all have to match the same few observational features. So we don't have a good way to see signs of another universe. On the other hand, that doesn't mean they're not there. There could be other universes, and we would never know about them. There could be universes that came before ours, and we would never know about them. So it's a long answer to a hard question.
Thank you very much for your answer.
And now it's turn to the question of our online participants. So Bogdan Novosadly, you are welcome. It's your turn to ask the question.
Thank you very much, Professor, for very interesting talk and exciting results from JWST telescope. My question is, I am from Ivan Franko National University of Lviv. I am a member of cosmology team. My question is, what do you see the disagreement between amplitude of cosmic microwave background power spectrum at highest harmonics measured by Planck and existence of farthest galaxies at redshift 15 or 17 discovered by JWST?
Okay, well, I don't actually have a good, sharp answer to your question. For the people that aren't familiar with this subject, if we know the details of the map that I showed you with the hot and cold spots, and we have enough fine detail, that we should be able to understand how the galaxies grow very directly. And if we get it right, then we should understand how quickly they grow. And so right now, I don't think we're ready to answer your question because it's just the very, very first days. But I think this will be a subject of great argument for many, many years. We already have indication that the galaxies grew much more quickly than we were expecting. And so that says something is wrong with our old picture. So, but first we have to know whether we've made a mistake in the observations. You know, I build instruments. I'm an observer, so I'm always thinking about the mistakes I might make. But we have to check everything. Thank you.
Okay, thank you very much.
Thank you. So the question from Lviv Polytechnic National University, the students from our university, you are welcome. Let's introduce yourself.
My name is Anastasia. I'm the first year student of Lviv Polytechnic University, and I would like to ask you the question. So our loneliness in the universe is very debatable, you know, and many people argue if the life beyond Earth existable. So if the JWST can solve this problem, this question, and what is your opinion on this?
Okay, so it's actually a very hard question. My opinion is that life is common in the universe wherever there is water and chemical energy available. Can we find out with the Webb telescope? Probably not. It's too difficult. We will be looking for planets that could possibly have those conditions. If we can find small planets the size of Earth and the right temperature to be like Earth and that have an atmosphere, then perhaps they are like Earth. But we do not expect to be able to see signs of life with the Webb telescope. We need to build the next generation of telescopes to be able to do that. In fact, American astronomers have said that's their top priority for the next great observatory after the Webb. So it would be about as large as the Webb telescope and more powerful, and capable of separating image of the planet from the image of the star, so we can do spectroscopic observations of reflected starlight. So you would be able to tell if that little planet has oxygen and water and methane and all the other things that make planet Earth. What is my guess? I think there's life out there. I don't think it's very much like Earth. I think most places we find life, it will be single cells, because that's what dominated Earth for 2 billion years.
Very much.
So are you satisfied of answer? So thank you. So from the online side, Shkil Alexander are eager to ask you the question. You are welcome, Alexander.
Thank you. Can you hear me? Yes?
Yeah.
Thank you for the interesting lecture. I'm undergraduate student of Warsaw University of Technology of Computer Science. I'd like to ask you a question. Is this easier for a Hubble telescope to collect light of lighter elements like gases, or does it collect also heavier light from heavier elements?
Okay, that's actually a chemistry problem. What wavelengths can be seen by each from each different atom or molecule, and where are those atoms and molecules? So if we spread out the starlight, individual stars, then we see the heavier elements like carbon, like calcium and magnesium and iron. Those are easy to see in the sun spectrum, and easy enough to see in other stars as well. Depending on the equipment and the wavelength that we care about, we can see many of the others as well. If we are looking into the interstellar space, not at stars, but at the space between the stars, then we have different choices, because only a few kinds of them are abundant enough to be seen. But I already showed you that we have neon and I think argon and sulfur can be seen in interstellar space because they emit light. So anyway, it's a hard problem, and the spectroscopic tool is very universal.
Thank you.
Thank you. So to keep gender issues, I would like to give a floor to the students from Lviv Polytechnic National University. So you're welcome.
Good morning. My name is Anna. I'm a first-year computer science student of Lviv Polytechnic. It was a pleasure to hear this lecture. My question is that James Webb Space Telescopes is gathering a lot of data every day. Throughout of all already obtained data, what was the biggest surprise you have not expected to obtain? Thank you.
Okay, a lovely question. I think the biggest surprise was how beautiful the pictures are. We knew that numbers would be good, but nobody can tell you what a picture will be like until you see it. Scientifically, the biggest surprise to me is that already we're seeing galaxies so far back in time, so far away. It says that galaxies grew more quickly than people expected. And so if that's still, if that conclusion is correct, then that's a wonderful surprise, because we just don't understand. And there's so many ways for nature to surprise us.
You see on our screen, we see two raised hands. So, and to Serhiy. Let's start from Serhiy Malinich. You are welcome to, you have a chance to ask a question.
Dr. Mather, thank you so much for your fascinating journey into space. And, I'm a professor at Lviv Army Academy, and I have just a simple technical question regarding the instrument itself. So the James Webb Space Telescope is located at Lagrange 2 point, which means that it always in the shadow, that sun's rays do not reach the instrument. So what is the power source for the instrument? Thank you.
Good question. Actually, we do not go exactly to the Lagrange point. We must avoid the shadow of the Earth. So we orbit around it. In fact, the radius of the orbit around the Lagrange point is about 600,000 kilometers. So we stay really quite far away from the Lagrange point, but it's okay. We still get all of the advantages of the Lagrange point, and we don't have to worry about the shadow.
Thank you.
Now I would like to give a floor to Dr. Kolomiis from our department. Welcome.
Hello, and yeah, thanks for the interesting talk. I will thank and complain that now there will be a lot of students during the lectures, what they have seen on the screen, because these nice pictures are actually carrying a lot of information, and it will be interesting for lecture and challenging to explain in the simple words what is packed there. And maybe philosophical. Big Bang is considered as the start of the space in our universe. So for me, it was always the question, can we say that the universe is infinite, or it's just as far as something has reached in the space?
Okay, actually, that's a fundamental question. So we can't prove, of course, that the universe is infinite. We can only say it seems to be without limit. So observation only extends a certain distance away from here because light has only had 13.8 billion years to travel since the expansion began. So whatever is beyond that, we would not know directly. On the other hand, there is no reason to think that the Earth and the Sun are in a special spot. So just as Copernicus moved the Earth from the center and put it orbiting around the Sun, now and cosmologists say, well, the Sun is not in the center either, even though it seems that everything is rushing away from us. We calculate that astronomers in other galaxies would also think that everything was rushing away from them. So the opinion and general assumption is the universe is infinite, without limit to space or time, and going. It does have a limit going back in time, but of course you cannot reach that limit. When you get to where time is extremely small at the Planck time, then you can't actually go there because the meaning of space and time are changed when it's so far back in time. So anyway, for another generation, I think, of theoretical physicists to make predictions that we could test.
Okay, thank you. So dear participants, dear Dr. So you see it's time to finish our event, our meeting. We are grateful for you, for your lecture, for the popularization of your scientific results. So we invite you to visit our university, our city. Our city is in UNESCO list, very beautiful, very ancient. And you see, we also have a very beautiful, our main building that we would like to add to this list of UNESCO. So you can see the beautiful picture of the famous Polish painter Jan Matejko. So we hope that we will find the time after the war to visit our city and our university. We have also our own observatory. So the few departments, they are interested in the similar question, in similar research. So you remember the invitation is still open. So thank you all participants for the activity, for your dedication to science. We sincerely believe that science will serve only peaceful purposes for the development of our countries, of all our world. So I wish you peace and love, and have a nice day. Goodbye.
Thank you. Yes, thank you so much for the invitation. It was wonderful to talk with you. And I hope to come to visit.
Дякую всім за активність, за увагу. Я сподіваюся, вам було цікаво. І завтра у нас буде ще один Нобелівський лауреат в сфері хімії.